Last week we talked about combinational logic circuits. We introduced Boolean algebra. We showed how to do manipulations on expressions. And if you have attempted this week's tutorial, some of you have already had tutorial today, you realize that things are not as simple as they may have seemed in the lecture. When we come to analyze a bit larger expressions or a bit more complex stuff, things get a bit tricky and the answer is not always obvious. So today we're actually going to talk about some way of overcoming these problems. And this is what I said. When we want to simplify expression and we want to come up with two-level design as a sum of products or product of sums, you can take the Boolean expression, you can manipulate it, but first of all, you don't always know what the next step is, and you don't know when to stop. I mean, you can never be sure, is there any simpler way to do it, or did we get to the simplest expression? So what we'll do today, we'll introduce a graphical technique called corner maps, which is a way to visualize Boolean expressions and extract the optimal sum of product or product of sums directly in a graphical way. Now, once you understand how things show up in a corner map, you will be able to relate it back to Boolean expressions, because things that, for example, I said in tutorials and in last week's lecture, they said some product terms, in a way, contain other product terms in them, which those who've done the tutorial today kind of understand what I'm talking about. But after today, it will become a whole lot more obvious. So just a definition, what is a corner map? Corner map, in a way, is a table. It's a table made of 2 to the power of n squares, and I'll draw one in a second, where n is the number of variables you have in your expression. Now, a corner map is a graphical way to represent Boolean functions. So if you have a truth table, you can apply the truth table directly into the corner map, and vice versa. From a corner map, you can go back to the truth table. Now, what you'll see is that when I draw it up, adjacent squares in the truth table, so any one of those 2 to the power of n square, each one differ from the one next to it by only one variable change. Again, it's a bit abstract. I'll draw one right there. And then once we draw the corner map and we recognize the patterns, then we can extract an optimal product of sum or sum of products. So what does it look like? Let's take, for example, a two variables function. So we have x and y. X and y, we said for two variables, we're going to have 2 to the power of n, so 2 to the power of 2, which is 4 squares. So it will look something like a table with 4 squares in it. Now, for each one of those squares, you will take some combination of x and y. So I will say that the variable x will take the values either 0, 1. The variable y will take either 0, 1. And then for each one of those squares, I have one of the 4 different combinations. Now, it's a convention to also write in corner maps the variables on the side to denote where the variable takes a 1 value. So you can see, and it'll make more sense once we go to larger corner maps with 3 or 4 variables. It'll become more obvious why we're doing this. But here you know that the variable x will take the value 1 anywhere in this column here. The variable y will take the value 1 in this row over there. Anywhere that I don't have a variable written in square bracket, similar to this row here or this column here, is the negation of the variable. So not x here, or in a way 0, and not y in this row here. Now, the idea is that once we have a function, we'll work with function in a second, we will fill into these into this square the value that the function takes for each possible combination. So in a way, it makes sense that if we have a truth table that have all the possible combination and the function values, we can just import it straight into the corner map. So this is a 2 variables corner map. Let me show you how 3 and 4 variable corner maps look like. So for 3 variables, we will need a corner map with 8 squares in it, where now we'll use the variables x, y, and z. So we'll use x, y here and z going down. And I will write all the possible combinations. So x and y will either take 0, 0, where the left 0 stands for the x, the right 0 stands for the y. And then 0, 1, then 1, 1, 1, 0. So I am doing it in a gray code manner. So I didn't go 0, 1, 1, 0, 1, 1 in a binary counting. I went in a gray code manner. Z will either take 0, 1. And then what I said before with the square brackets, I will denote where each variable takes its true value. So x will take its true value in these 2 columns here. Y will take its true value in these 2 columns here. And you can see it where in the right 2 columns, x takes the 1. In the middle 2 columns, it's y that takes the 1. And there's some overlap between x and y, as we expect. And z will take its true value here. Now, a 4 variable corner map, obviously will have 16 squares in it. And we will now use w, x, y, z. And I will again write all the possible combinations in a gray code manner. So 0, 0, 0, 1, 1, 1, 1, 0. Similarly down here. And I will write where each variable takes its true value. So we haven't filled in anything into the corner maps yet. This is just the structure of the corner maps. So how do we actually use it to simplify expressions? Let's take some simple function with 2 variables, a and b. And I have the truth table here for the function. I've got all the possible combinations, and I can deduce the function values right from the expression. Now, if you're observant, you can see these are in fact mean terms of the function because we have all the possible variables present. Not a, not b will correspond to the combination 0, 0. It's only when both a and b are 0 that this term here will be true. So the function will take a value of 1 there. A, not b stands for the combination 1, 0. So that's that one here. And then when neither of them is true, then the function just takes the value of 0. Now, if I've done it using Boolean algebra, this one's a fairly easy one. I would probably vector out the not b, do not a or a, which goes to 1, and simplify it to not b. And you can, by the way, with this sort of simple expression, you can look at the truth table and you can see in fact that anywhere that b is 0, the function takes the value of 1, and 0 anywhere else. So that's a fairly simple one. How do we actually represent it in a corner map? So we said 2 variable corner map is a table with 4 square with all the possible combination. And then we read one by one from the truth table. So where we have the combination 0, 0, the function takes the value of 1. When we have the combination 1, 0, this one, the function takes the value of 1. The combination 0, 1 is 0. and the combination for 1, 1 is 0 as well. Now, what we're trying to do is now find patterns in the corner map. And we're trying to group as many ones as possible together. In this case, these two ones are next to each other. Let me use another color for this, maybe green. Does it make a difference slightly? I will circle those two ones. And now what I'm going to do, and this is how we treat corner maps, is find the common variables that always take the same value for all the ones in the group. In this case, it's variable b that will always have the value 0 for both ones. So I will include it in my expression. So not b because it's where b takes 0. Where the variable a actually spends, it can either be a 0 or 1. Any variable that the group spends more than one of its values, either the 0 or 1, so if it covers both values, I just omit it from the expression. And this is how we work with corner maps, and I'll show you when we work with larger corner maps how it all sort of fits in nicely. So same idea, we'll take it with a function of 3 variables. And now I specify the function in the sum of mean terms shortcut notation. And in this time I will go through the truth table, although we don't have to. I'll show you in a second how we skip that stage. So to fill up the truth table, we know that the function takes the value of 1 at indices 0, 1, 2, 3, 4, and 6, which will be 0, 1, 2, 3, 4, and 6, and 0 anywhere else. Then we can take a corner map of 3 variables. So we have A, B, and C. Where A is here. And this will now become apparent why it's so convenient to write out those square brackets. And then I will fill in the values from the truth table. So 0, 0, 0, the function takes the value of 1. 0, 0, 1, it's a 1. 0, 1, 0, it's a 1. 0, 1, 1, again a 1. 1, 1, 0, which is down here. So just realize that we sort of went sequentially, but then all of a sudden we jumped down here. So make sure you're very careful when you're copying values from the truth table into your corner map that you don't just go by order, because it's not always by order. Once you get used to how corner maps are ordered, you will start doing it more automatically. You'll know the order, and you'll see once we go to 4 variables, things start to jump around. It's something you get used to the longer you work with it. So 1, 1, 0 is actually down here. Again, it's a value of 1. 1, 1, 1 takes 0. 1, 0, 0 takes the value of 1. And 1, 0, 1 takes the value of 0. Now we want to circle the groups. What I didn't tell you before is that the groups that we circle must be groups that are power of 2. So they must contain either 1 variable, 1, 1, 2 1s, 4 1s, 8 1s, or 16 1s. So it must be a power of 2. And it must be a rectangle. So I can't, well, first of all, I couldn't just circle the whole group together because 6 is not a power of 2. And it wouldn't be a rectangle. So what I'll do, I'll circle 2 groups. One of them will be this one here. Still not too much of a color change, maybe this one. And the other group will be another rectangle here. which is another group of 4. So both of them are valid groups because they're both power of 2. They both have 4 elements in them. And then, like before, I go group by group and I start seeing what's the missing variable in each group of variables, one variable or a few variables, and then those that have more than one value for a variable, I just omit it from the expression. So if I look at this group here, those 4, then I can see that A is always going to be not A. And again, this is when the square brackets come in very handy. B will take either the not B or the B. So it changes its value, so it's not going to be in this term. So I said I have not A. And also C takes both C or not C in this group. So it's really just not A that's the common value for a variable for all the group. Now the other group, the blue one, has changing value for A, changing value for B, so I'm omitting them out, but it's always going to be not C. And what I do, I OR the different groups together. And this will give me the optimized sum of products expression for the function. And you can verify this. You can see that anywhere that A is 0, the function will take the value of 1, or anywhere that the function that C takes the value of 0. So anywhere that C takes 0, and those will give us this simple expression. Here.
Why does this work?
Because it's based on this theorem there, xy or x not y is x. And let me draw it for you again. So essentially what we're doing, x, y. Now this function there, xy or x not y, will either be xy is this term here, x not y is this one here. These will be zeros. So essentially each one of those ones will contribute a mean term into your, if you just, in a way, circle just one square, you get a mean term out of this. Now, if you write those mean terms, you can use Boolean expression, Boolean algebra, to simplify it using this theory here. And this is based on the fact that you have the common vector, but you have the variable that changes its value. And therefore, it will always be 1, and then you end up with just this one. And this works as you get the groups larger. This is the same theory. You can go step by step by step and eliminate one variable every time. So this is why it works. Now, when working with Karnaugh maps, the way I group the groups, so this one is really this group here. And as you can see, it's only really when x takes the value of 1. Now, Karnaugh maps also work in a wraparound manner. And I'll show you an example in a second, where you can sort of start grouping. Well, it doesn't make sense with 2 variables, but I'll show you an example with 4 variables, where you can go off the end of one end and come back in a wraparound manner. Now, the only other point I want to emphasize, K-maps or Karnaugh maps are easy to draw when you have up to 4 variables. So I showed you how to draw it for 2, 3, and 4 variables. You can work with 5 or 6 variables, but you start getting into 3-dimensional structure. So if you want to imagine it for 5 variables, you will essentially have sort of 2 structures. Each one have 4 variables, and you can imagine that they're sitting one behind the other. So you can start circling groups by going into the page. So this one will correspond to this one into the page. And then with 6 variables, you're going to have 4 of these. You're going to have 4 of them, one behind each other, and then things start going into the page. In reality, we usually work up to 4 variables because 5 and 6 get very messy. And there's no really way to draw it for more than 6 variables, not on paper anyway. A lot of the optimization algorithms in the CAD tools are based on this idea of corner maps, although once you put in a software, there's no problem going to as many dimensions as you want because computer program doesn't draw it on paper. They can just expand it. Okay. Now, I want to show you the wraparound example, but before I do, I want to show you how we can go directly from a function that's given as a sum of products, sum of mean terms notation, directly into the corner map. So obviously, we want the function to have the value of 1 for any index that exists in the sum of mean terms. And you could go, all right, this is 0, 0, 0, 0, so that's 0, which means the function will go 1, and then you can go 1 by 1 by 1. Or you can, in a way, memorize or observe the patterns in this corner map. And the indices, if you go AB being at the top and CD being on the side, the pattern will look like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, this is something that I know this order because I worked so much with it. You will be good and will simplify your work if you do remember this. It's not that hard to remember. But you can always deduce it just by looking at the corner map, because these indices here really just correspond to the combinations on the top and on the side. For example, this 8 here is 1, 0, 0, 0, which is binary for 8. So now that I know how to relate those two together, I can fill in the corner map with the corresponding ones. So again, for any index that exists here, I will have a corresponding 1, and then all the rest of the places I will fill them up with zeros. Now I want to make groups. I want to make the largest group possible. The larger the group, the more, every time you double the size of your group, you're omitting a variable from your final solution. So if you only circle 1 square, it will be a min term. It will contain all 4 variables. If you manage to circle a group of 2, it will have 3 variables in it. If you manage to circle a group of 4, it'll have 2 variables. Group of 8 will have 1 variable. And if you manage to circle the whole corner map, it essentially means you have a constant 1 or a constant 0. Well, if you circle the whole thing, it's a constant 1. Now let's see how we can, what we can do to circle the largest groups. We have a very obvious group of 8 up here. Now we also have those 2 here. Now I'm very tempted to circle those 2, but then I remember that I just said that corner maps can wrap around. So I can essentially group those 2 with those 2 here. I'm not allowed to group those 2 with all the 4 up there. I'm not allowed to keep going because it must be a power of 2. So I can't have a group of 6. Now, I'm looking at this one here. Again, I'm very tempted to just circle it by itself because all the surrounding squares are zeros. But then I remember that I can wrap around and group it with this one. And I think, okay, I've got a group of 2. But then I remember that I can wrap around to the sides as well. And I realize that this one here can actually be grouped with this one, and this one. So it is a 4 group that comes from the corner. I'm just wrapping around twice. Once to the side and once top to bottom. Now I managed to cover all my ones in the map, and I can start reading out the expression, just like I've done before. I will start off with my largest group, which was this group of 8 here. And I can see that A changes its value between different sections of the group, so it's going to be omitted. So does B. C, however, is always going to be in its negated form. So I'm always going to have not C. And I can see that D sometimes take value of 1, sometimes the value of 0. So I am left with only not C. Which makes sense, because remember I said if we have a group of 8, we expect to only have 1 variable when we talk about a function with 4 variables in them. Now, I'm not finished just yet. I'm looking at the other group. I will look at this one that wraps around. And I do go variable by variable, and I test it. So variable A is always going to be in its negated form. So I do have not A. Variable B changes between different sides of the group. Variable C changes between different sides of the group, between those two and the ones at the top. But variable D will always be in its negated form. Both here and up here, it's always going to be not D. So I end the two variables together. So I have not A and not D. And then I remember I had one other group, the one that goes in the corners. A does change its value because this one is A, this is not A. So we leave it out. B will always take its negated form. So I do have not B. C sometimes will be in its true form, and then up there it's in its negated form. I leave it out. And D will always be in its negated form. So I do put it in. And this will give you the simplest possible expression for sum of products for the function. Any question? Yeah.
So what, only the n bits can wrap around. Like for example, in the second column,
Yeah.
you can't wrap those around. The one up the top and the one down the bottom, you can't wrap them around.
These ones, or
Yeah. No, I mean,
between.
the 0, 1, yeah, that one, and the one right down. No, not that one. The one across that one. So you can't wrap them around.
With
Just like you did on the end point.
I could, and I could. I mean, I did wrap this around to the top there, if that's what you're saying, or because on the side you don't wrap around because you've got stuff on the side. The only place to wrap around is to go sort of down and then come back from the top, which is what I've done. Or am I not understanding you? Do you want to come up and show me?
Just so here on the endpoints, we've wrapped this single one with that single one.
And
Can
with
we wrap
and
this
with
single?
this,
Can we wrap this single one with that single one?
I could.
You could.
Yeah.
But it wouldn't do it.
No, I could, and I'm getting there in 2 slides from now. What I'm trying to do is find the largest groups possible. I mean, I could just wrap this with the one up there. If, for example, this one here was a 0, then I couldn't, in a way, group it together, and I had to just wrap this around with this one, which is what I could do. The reason why I expanded it is because I'm trying to have the largest groups possible because the larger the groups are, the less variables I'm going to end up with. If I only wrap this one with this one, I have a group of 2. Group of 2 will mean 3 variables in this case, where because I expanded it to be as part of a group of 4, I do have only 2 variables instead of 3. I will make some more definitions in 2 slides, and we'll talk about this. Yeah.
So how do you know if you're not missing anything?
In 2 slides. Yeah? Before we answer those 2 questions, I want to give you another example that is not, well, it's slightly straightforward, but there's a slight complication as well. If we, I'll go with this blue here. I have a function with 3 variables, and I have a 3-variable Karnaugh map. By the way, as a side note, the way I draw my Karnaugh maps with A, B at the top, and C on the side is my convention. Well, it's not just mine, but it's a convention. There's no stopping you from writing A and B on the side and then C on the top, and then you will end up with the Karnaugh map. Can you see the blue? With a Karnaugh map that looks like this, where this will be C, this will be A and B. B. Another way some people write the Karnaugh maps, for example, is putting A here and then B, C here. Now, one thing to understand, it doesn't matter how you order your variables or what shape you give it, as long as you're consistent. If you chose to draw your Karnaugh map like this for some reason, and I will not be very happy with you in an exam because I like to mark things that I know. No, I do know this. And as long as you're consistent, as in you will always use A to be here and B, C here when solving it, you will reach the same final result as if you drew the map like this. So how you draw it, it's up to you. Some people prefer it that way. I personally prefer it that way, and I prefer if you've done it the same way I do. But it wouldn't be incorrect if you've decided to do it otherwise. So back to this Karnaugh map here. I've already put in the values for the function. Again, using the indices 1, 2, 3, 4, 6, 7. No. 6, 7, 4, and 5. And I put up the ones in there. Now I want to find all the biggest groups possible. So this one here, I can group it with this one here. And I couldn't go any larger because the next group size would be a 4. And I couldn't go any further to the right, and I couldn't go up because there's a 0 there. Another possible group will be the one up here. And again, I can't go any larger than this. This one here, I can actually wrap it around with this one. Are there any other groups I can make? Yeah? Yep. There's another group right here. Those 2, I can group them together. And I could have started by grouping this one. Now, if I try to write out the expression for this one, what I will find is that I have redundant terms. Because even without this group here, I've already covered all the ones in my map. And adding any further terms will actually will be redundant because they don't add any new information to the function. So there comes the question of how do we know when's the best solution and whether there's a systematic way. For this, let me make some definitions for you, and I will read it straight from the slide. A product term is an implicant of a function if the function has the value 1 for all mean terms of the product term. A prime implicant, another term that we have, is a product term obtained by combining the maximum possible number of adjacent squares in the map into a rectangle with the number of squares being a power of 2. A prime implicant is called an essential prime implicant if it is the only prime implicant that covers one or more terms. That's what I thought when I first read it. So let's see a bit of an example, because this is a mouthful of definitions. I'll start off with showing you what an implicant is. An implicant is any group of ones that makes a power of 2. For example, if I group those two, that's an implicant. If I only grouped one square, that would be an implicant. If I extend this group here and I wrap it around to include this one, it will also be an implicant. So really, any valid group that we can make is called an implicant. A prime implicant, let me write down, so that's implicant. What we call a prime implicant is an implicant, or a group, that is the largest possible group we can make. So, for example, this group here will be a prime implicant, because I cannot extend it any further. If I, for example, just took those two here, then it would be an implicant, but because I can expand them up, then it wouldn't be a prime implicant. So a prime implicant is an implicant that is the largest possible group. Prime implicant. Then the third term we came up with is an essential prime implicant. Essential prime implicant is a prime implicant that has at least one square in it that cannot be covered by any other groups. If, for example, let me use another color. If I look at this group here, which is a prime implicant because I cannot make it, bless you, I cannot make it any larger. So it's a prime implicant. But I can cover all the possible ones in it by using other groups. For example, I can have this group here, which will cover those two ones. I can have another group that groups those ones together, which will use these ones. So then, if I then go and take this group here, together with the group from the corner, the wraparound one, in a way, I wouldn't even need the red one, because I covered all the possible ones, and I won't need it in the expression. An essential prime implicant, which is what we have in the middle, for example, is a prime implicant that cannot be covered entirely by other groups. And you can see it why this is a prime, essential prime implicant, because, for example, I could cover those ones with this group. I could cover those ones with this group, but this one here is unique to that particular, where are we? To that particular prime implicant. Now, if I have at least one square that cannot be covered by other groups, that's what we called an essential prime implicant. So, essential There you go. Essential pi implicant. And this is the definition of the essential, that we have at least one. We can have more than one, but at least one. Now, why do we need those definitions for? Because now we can come up with an algorithm, a systematic way to find the best expression. And the algorithm goes like this. Find all the possible prime implicants. So group all the possible groups in your map, or all the possible largest groups that are power of 2 in your map. Then, in your solution, in the expression, include, for a starter, all the essential prime implicants. So all of those, similar to the example before, that must be in the final solutions, because otherwise they will not be covered by any other group. So include them in the expression. Then, after you've done this, you obviously, well, not obviously, you may end up with few ones that are not part of the essential prime implicants. Then we start including the other prime implicants that we have. So groups that, so we're including ones that may be covered by more than one group. But what we're trying to do in order to get the optimal solution is to minimize the overlap between the prime implicants. Let's see an example of how we go about doing this. So here's a Karnaugh map, and it has to simplify it. And then we start looking at possible groups. And I might do it in fancy colors. So let's see, we have a group down here. And again, I'm trying to find the largest groups possible, so the prime implicants. I have another group here. And I'm trying to find all of them. I don't care about optimization just yet. I have another group here, bless you. And then another group here. And as you can see, I can actually make quite a lot of groups. Can make this group here. And what about this one? Can I group it with anything? No, so it's by itself because I can't wrap around, I can't group anywhere else. Now let's try and find all the essential prime implicants. Now from this drawing already, you can identify which ones are the essential ones by looking at those groups that don't have more than one thing surrounding them. Obviously, this one here will be an essential one because that's the only square that surrounds it. This group here will be essential because the left one in the group is only surrounded by this particular group. In a similar way, this one here only has one group, so it will be this one here. This is essential as well. And I think these are all the essential ones. So we start off by writing them in our solution. So let's start with this corner here, which corresponds to node A, node B, node C, node D. And as we said, when we have one square, it's going to be all the possible variables. And they're all complemented just because it's the combination of 0, 0, 0, 0. Then we look at the next group. Let's take this one. So we're including all the essential ones, which will be node A, C, D. So we got this one covered. We have this group here. Can you see? Yep. Which will be node A, B, and what we have, node A, B, and D. And we have this one group with this group here, which is A, C, and node D. However, this is not the end of our expression because we only accounted for the ones that are marked yellow, we still have this one here that's not accounted for. Now for this one, we have a choice now. Either to use this group here that we grouped with the red, or use the green group. So we can choose either one, it doesn't matter. If we choose this one going down, we will have A and B and C. If we choose the one going across, we'll have B and C and D, and we can choose either one. Now in this case, it doesn't matter which one we choose, we will end up with the same complexity for the circuit that we're trying to build. All right, any questions about corner map so far? All right, in that case, let's take a 10 minutes break. And we'll continue after the break.